We're going to move on now to Dr. Dustin Poppendieck from NIST. So Dustin, if you're here, he's going to use, he's going to talk about using CO2 as a ventilation clue. So Dustin, over to you. I can see your screen.
All right, can you hear me?
And I can hear you. Perfect, thank you.
All right, great, thank you. Thanks for the invitation. Let's see if I can get my computer to advance. Okay, so before I start, I just wanted to note that any guidance that I present today is not a recommendation or endorsement for my employer. And second, I'm from the US, and so some of my reference today will be US specific. I'm sorry I was not able to make them a little bit more specific to your scenarios. So just want to start out with, in the era of COVID, we really want to find and fix classrooms that have inadequate ventilation to reduce the possibility of long-range transmission. We've got COVID-19 latent particles. Oh, I got some auto advancing going on. COVID-19 latent particles can build up in spaces with poor ventilation and lead to infections. Historically, there's limited available data that's shown in the US that we have underventilated classrooms in relation to pre-pandemic standards. On this graph here shows for typical classrooms, the required ventilation rate for outdoor air is about 7 liters per second, which is where this vertical line is. And a majority of the classrooms in this work surveyed by Hannibal Shaughnessy in 2010 were far below that 7 liters per second per person in these classrooms. So what our goal is of using CO2 meters in classrooms is really to find these poorly ventilated rooms and, more importantly, fix them, either from a ventilation standpoint or using filters. So let's start off with backing up and say, well, where does CO2 come from? And if we think about it, CO2, your lungs exchange oxygen and air with carbon dioxide. And importantly, that amount of carbon dioxide that we emit really depends on the sex, the age, and the activity level and size of the people in the room. The air you breathe is about 0.04% carbon dioxide, and the air you breathe in, and the air you breathe out is about 4% carbon dioxide. So given that relatively high concentration and relatively ease of measurement to other chemicals in the room and what we emit, carbon dioxide is really a good proxy of general emissions from humans. And I want to take a pause here and note that CO2 is only a proxy for human emissions. There's many other things that impact our indoor air. We have building materials, furniture, cleaning supplies, indoor chemical reactions, outdoor contaminants. All these things impact indoor air quality. And so hence, low CO2 concentrations don't necessarily mean that we have good indoor air quality. If we're going to use consumer grade CO2 monitors to monitor our classrooms, we have to realize they have some limitations. Monitors that don't use non-dispersive infrared sensors can have errors depending on how they're calibrated. And although these NDIR monitors report values to 3 digits, they're typically only accurate to about plus or minus 50 ppm. And finally, these sensors can drift over time. So the sensors, even though they're typically linear, the difference between the indoor and the outdoor, the delta, is typically fairly constant for these sensors. So we just need to be aware that these sensors aren't perfect, but they're still really useful to help us look at ventilation. So we also need to make sure when we're talking about CO2 that we don't have other sources of CO2 in the classroom that are non-human, such as indoor combustion, vehicles idling outside indoor air takes or windows, or significant removal mechanisms such as huge numbers of plants in the room, like a greenhouse, or specialty filters. So what can we do with these CO2 readings in the classrooms? How do we identify poorly ventilated classrooms? So there's 3 really potential approaches we can take. The first one deals with how much air we rebreathe that has previously been in other people's lungs. So we can use the CO2, this is what we call the rebreathed fraction, and we can use CO2 to determine the fraction of air that we're rebreathing. For instance, if the average outdoor concentration of carbon dioxide is 800, indoor concentration is 820 parts per million, and the outdoor concentration is 420 parts per million, then the exhaled concentration, and the exhaled concentration is 40,000 ppm, then 1% of the air, every breath you take in that room, will consist of air that's been in somebody else's lungs. If the air concentration is say 3,600 ppm, then 8% of every breath you take is going to consist of air that has been in someone's lungs, or 8 times higher than if the average had been 820. For airborne viruses, we want to keep that rebreathed fraction as low as possible, as indicated by the carbon dioxide concentration. So the lower the rebreathed fraction, the lower the overall risk if there's somebody, a COVID-19 emitter present, and that lowers our risk of that we would inhale COVID-19 laden particles. The second way that we can deal with CO2, approach CO2, using CO2 readings in the classroom, is by examining what I call the maximum daily CO2 concentration when the space is normally occupied. So when we have students in the room. I've looked at data from school districts here in the US where they've measured when people weren't in the room. And so that does not really useful as far as a metric of examining ventilation. We need to have it under normal occupancy. So to do this, what we're going to do is we're going to take the CO2 sensors and we're going to put them outside for 5 minutes just to check to make sure that they're getting 400 to 500, make sure that they're working properly. They're not reading 3,000. Then we need to make sure that the room that we're measuring is occupied with normal occupants and normal use patterns. They're not having a dance party the day that we're doing it when they normally are just sitting there calmly. And then we need to locate the sensor somewhat in the middle of the room and log the data for a full day. And we need to note that the ventilation will change depending on whether the windows are open, the season, the weather, the thermal loads, and if you have any kind of central HVAC. So we need to repeat the measurements. Just doing it one day is not necessarily going to get us great insight on how that ventilation is working in that room. So here's an example. The CO2 data from my son's school, actually. Carbon dioxide concentrations essentially will build up in the classroom over time when the students are present and drop when they're absent. And this is why we can't just take one point during the day, rather we need to log for the entire day. In this case, you can see when the kids enter the room at 7, went out for recess around 11, and the peak concentration after lunch, which would be, if you would just take one measurement, you would get a very different reading for those single points all day. So this is why we want to measure for the entire day and log the data. The data of interest in this case is the highest average value of approximately 15 minutes. In this case, it's somewhere between about 1200 ppm or about 800 ppm above the outside background concentration. These data come from a portable classroom that was at 2100 ppm before the teacher was given a CO2 monitor. Once they were given the monitor, they actively opened the windows and doors to reduce the CO2 concentration. And they also have an exhaust fan that they can reduce the concentrations even further if they'd like. So how do we use maximum CO2 concentration data to get an idea of ventilation? What we can do is we can model what the concentration should be under typical design uses in the classroom. So to do this, we need to know the volume of the space, the designed ventilation rate, what we're targeting, the activity level of the students and the teachers, along with the number, sex, age, average weight of all of those students. The activity level is described as a MET level, and it's a description of how much the people in the room move and their energy, relative energy use. And this can vary a lot depending, which can lead to a lot of uncertainties in this approach. There are some other assumptions. This model includes a steady state assumption for the occupation and ventilation rates. And it's, while it's not great for all spaces, its assumption is reasonable for classroom activities and for the classroom activity and number of kids present tend to be relatively consistent on the time scale of this model. Even if the space never reaches steady state, the high maximum values can be used to indicate problematic spaces. Another issue is that the model assumes that all air entering the space is from outside, like hallway and hallways and adjoining, not from hallways and adjoining classrooms. And while this may be true for portable classrooms, in school buildings, it may not be, in which case the model may under or over predict the CO2 concentrations. So NIST has a web-based single zone mass balance tool that allows the user to determine what the CO2 concentration would be if the school density and activity scenarios are as designed. You can just search for CO2 NIST web tool and you should be coming up with it. And what this tool does is it allows you to put in a number of parameters, including various ventilation rates, design ventilation rates, and various activity levels for each age group. In this case, we're modeling, whoops, it wasn't supposed to be 18 to 29-year-olds. It was supposed to be 3 to 9-year-olds. But I have the slightly wrong, I cut and paste the wrong data file. And then it will give us a results where it will show us what the concentration will be over time, including when the maximum concentration is reached at some given in time. So now we can actually figure out what that room should be if it's operating as it normally is. So on this graph, we can see how the CO2 concentration is a function of the ventilation rate. For all all case sizes in this, the class size, student activity levels, number of students are held constant. And you can see at high ventilation rates, which are greater than pre-pandemic requirements, shown on the black line, the CO2 concentrations are reached steady state relatively quickly in the first 1 to 2 hours at a relatively low level, below roughly 700 ppm. And this is an example where the low ventilation rate, and in this example, the low ventilation rates and the concentrations may continue to rise all day, reaching concentrations that are maybe 3 to 4 times higher than we'd see in pre-pandemic guideline values. And those would be the red lines up here. So we can see if the classroom hits 1250 ppm after 2 hours, it's likely not going to be meeting the appropriate ventilation rates. Sorry, but if it was designed, Likewise, if the concentration is still rising after 3 hours, if it's still increasing after 3 hours of uninterrupted occupation, then it's also likely not reaching pre-pandemic ventilation rates, as higher ventilation rates would have reached stable concentrations earlier. Here's an example of a real classroom. The CO2 concentration is still rising after 3 hours of uninterrupted occupation, despite only having a maximum CO2 concentration of 1600 ppm. It likely would not be meeting pre-pandemic ventilation rates. However, if the classroom is below 800 ppm after 4 hours, it would likely be reaching those pre-pandemic ventilation rates. So we can summarize the relationship between ventilation rates and the maximum steady state concentration in the classroom. And this is a chart for 34 14-year-old students and one teacher in a 100-meter square classroom. The purple line shows the potential maximum CO2 concentrations for the students and teacher have minimal activity, so that they have low MET values. The green line shows the same potential maximum CO2 concentrations if the students and teacher have high MET values. So the only difference between these two lines is how active the students are. And you can notice that the current ASHRAE requirement here in the US is that they should have 6.7 liters per second per person of ventilation. And you can see that the maximum CO2 concentration for those two different MET rates could be anywhere from 800 to 1250 ppm, depending on the activity level of the occupants. We can do the same thing for 24 7-year-old students in a 100-meter square classroom. In this case, if the room was operating at the ASHRAE requirement of 7.4 liters per second per person, the maximum CO2 concentration could be anywhere from 685 to 950 ppm, depending on the activity level of the students. So if we overlay these two rooms, it gives us a real sense of the uncertainty in modeling due to the activity level, the age, and the number of students. Despite this uncertainty, though, we can still draw some conclusions. If we have high maximum daily, if our maximum daily CO2 concentrations, high maximum daily CO2 readings are going to still be indicative of low outdoor ventilation rates. If the maximum CO2 readings are below 700 ppm, we can be pretty confident that our ventilation rates are sufficient, especially if the readings are repeated over multiple days. If the maximum daily CO2 concentration readings are above about 2000 ppm, we can be fairly confident that these ventilation rates are going to be pretty low, and these rooms should probably be inspected and addressed. And these are the classrooms we're really trying to find, is classrooms that are going to hit above 2000 ppm per day. And the range of these values gives us less conclusive, the range in between say 800 and 2000 gives us less conclusive information on the state of the ventilation, as the model assumptions, the age, the weight, the size, the activity level, whether or not the room's at steady state, all impact the conclusions we can draw from the data. So the bottom line is we have some dichotomy here. Below 800, we're probably doing great. Above 2000, probably have a problem. In between, we don't really know. And here's an example illustrating use of a CO2 monitor in a classroom to demonstrate that it's poorly ventilated.
Just a couple of minutes left, Dustin.
Okay. So basically, they found really high concentrations. We're just the fault of 2 faulty air handlers. And the moral of the story is if the maximum concentrations are above 2000, steps should be taken and should be taken immediately, including checking the equipment, evaluating the room use, whether the density activity levels are as designed, and ensure that there are no other sources of CO2 analysis that could be complicating the analysis. There's a third way we can also do this. We can look at the air change rate. I'm going to go through this relatively quickly. Once the room is unoccupied, you can look at the decay of the CO2 concentration over time, and that decay can give you an estimate of the air change rate. You can do a bunch of fancy math, plot it up, and you can get the slope. Inverse of the slope is the air change, as the decay rate, which can be used as an estimate of the air change rate. This has a bunch of limitations that I'm not going to go into today, but you could spend more time on this if you'd like. In this case, the decay rate in this classroom was 1 per hour. A lot of people like to hit 3 to 6 per hour in classrooms, or 5 to 6 per hour in classrooms. And this one, when the windows and doors were shut, it is all the way down at 0.2 per hour. So this classroom has very poor ventilation when the windows and doors are not open. What can we do with that data? If we do determine an effective decay rate, we can determine an effective particle decay rate. And this is the combination of the ventilation rate, any removal from portable air filtration, and any removal from central air filtration. And we can add these values up and determine our overall effective air change rate. I'm not going to spend much time there. I'm going to wrap up with 2 other things. I really want to highlight the fact that if you're measuring CO2 and other parameters like RH and temperature, it allows you to build trust with the school community. And this is an example of Boston Public Schools, where they're currently monitoring over 4,000 classrooms in real time. The data is displayed on the internet. It allows immediate identification of problems and prioritizing of resources to repair those classrooms for both replacement, and also provides data to staff to support any issues and complaints they have with indoor environmental quality. Finally, as Mark mentioned before, there's a lot of ancillary benefits of improving ventilation, including improved test scores, cognitive function, while reductions in absenteeism and respiratory symptoms. So bottom line, CO2 concentrations in classrooms vary. The measurements should be repeated as season and heating and cooling operations change. The measurements do, however, provide actionable data that schools and teachers can use to minimize risk, and high values should immediately be investigated to address potential issues. Low values are not a guarantee of no risk, but are safer than higher values. Finally, open access to CO2 data can build trust between the school community and the building operators, and open data allows the targeting of community resources to address problematic spaces. And one last point is that classrooms with high ventilation levels can lead to long-term benefits for students and teachers. Thank you.
Thank you very much, Dustin. That's very interesting, and it's good to get a perspective from across the Atlantic. We have several questions in the chat, but just one from Tom Sturgeon, which I'll summarize to say, how well do you think the well-mixed approximation works in classrooms? In other words, taking a value from a single point, perhaps miss pockets where concentrations are higher than the average?
That's an interesting question. And if we were talking about a more dynamic space, I think that would be a valid concern. But when we're talking about a space that the students tend to sit in for hours at a time, the well-mixed assumption becomes more and more valid over the time frame of which we're looking at. So if we're looking at 1 to 2 seconds, yes, that's not that much of a concern. I mean, that is a big concern of well-mixed assumption, but in reality, these students are sitting in the rooms for 4-6 hours at a time. And over that time, if you average most of the room is going to be fairly well mixed. There will be occasional spots near corners and bookshelves and things like that. And you want to avoid those spaces when you're monitoring.
Okay, thank you. Well, thanks very much again. A very interesting talk.